All right, guys. So in this video's lesson, what we're going to talk about is how you can actually graph complex numbers. Now, in order to do so, we're going to have a new type of number plane, which is going to be called the complex plane. So when you're graphing on the complex plane, the first part is let's talk about how the x and y axis are going to be slightly different. So the x-axis is going to represent the real part of your imaginary number, and it's going to be called the real axis, which oftentimes we abbreviate to just be RE. The y-axis then is going to be the imaginary axis, which we will abbreviate IN. And then when we want to graph a complex number, such as a plus bi, that's going to go on our complex plane as the coordinate a comma b. Now, here's where you can actually talk a little bit about kind of the difference between a real number, a pure imaginary number, and an imaginary number. So if you remember, a real number is a number just like the number 3. As a coordinate then, that would become the point 3 comma 0. So that would be the point right here on the complex plane. So notice that all of the real numbers can actually be plotted in the complex plane. You can also have an imaginary number like 2i, which we would consider to be a pure imaginary number. And the reason for that is when you graph it, that's going to represent the coordinates 0 comma 2. And so notice that that point is only going to be on the imaginary axis at the point 0 comma 2. So then imaginary numbers, like let's say 1 minus I, are going to take the form of the point 1 comma negative 1. And those are going to be where it's actually somewhere in the plane. So 1 comma negative 1 would give you a point right here. So a real number you would have just on your x-axis, the real axis. A pure imaginary number you would just have on the y-axis, the imaginary axis. And then an imaginary number you would have just somewhere else in the plane. Let's do a little bit more practice with this. So number 1, graph each of the following complex numbers in the complex plane. I'm first going to rewrite them as a point, so 3 plus 4i can be represented as the point 3 comma 4. And then to graph that, we do that like normal. That would be this point right here. So the next point, or for the next complex number, negative 1 plus 5i, that would become the point negative 1 comma 5. So that would be this point right here. Finally, for C, negative 5 minus 3i, that would become the point negative 5, negative 3. So that would be this point right here in our complex plane. So graphing complex numbers is pretty easy. So let's talk about a couple of other parts to this that kind of make it a little bit more interesting. Let's start by talking about what's called the modulus of a complex number. So the modulus of a complex number is its distance from the origin. So let's kind of visualize what that's going to look like using A as an example. So our distance from the origin would be this distance right here. Now, as we consider that distance and how to find it, we do have our distance formula from geometry that we could use. However, there's going to be kind of an easier way to think about it. If we want to know what that distance is, really all we have to think about is the fact that we went over by this much, that distance of 3, that was A, and then we went up by this distance, which actually, if you think about it, is represented by your B value. And thinking about this as a right triangle, if we want to know this distance, all it comes down to is Pythagorean theorem. A squared plus B squared equals C squared. And if we want to know just what C is, and oftentimes we'll call that R, so let me rewrite that as R, then R would just be equal to the square root of A squared plus B squared. So that would be our modulus. Our distance from 0 has a pretty simple formula that we can use to find that. So let's go ahead and practice finding the modulus for the complex numbers that we graphed above. So for 3 plus 4i, we had A was 3 and B was 4. So if we want to know what the modulus is, R is equal to the square root of A squared plus B squared, which, as we simplify that, becomes becomes the square root of 9 plus 16, which is the square root of 25, which ends up being a whole number, which is 5. Let's do the same thing with our next one. So we had that a was -1, b was +5. So our modulus, our distance from 0, would be a squared, which would be -1 squared, plus b squared, which is 5 squared. Be careful with typing those in. If you choose to use a graphing calculator, -1 squared is +1, 5 squared is 25. And as you simplify that, that becomes the square root of 26, which is the exact answer. There's no way that we can simplify that. If we wanted to get that as a decimal, though, to the nearest tenth, that's about 5.1 units away from the origin. Let's do one more example. So in our last example, a is -5, b is -3. So if we want to know the distance from the origin, the modulus for that complex number, we're going to take -5 squared plus -3 squared and take the square root. So that would become the square root of 25 plus 9, which is the square root of 34. And again, that would be, if you were asked to leave it as an exact answer, where you would leave it. But if we want a decimal approximation for about how far that would be, this would have a modulus of about 5.8. All right, so the last thing to talk about is what it looks like when we graph complex numbers and when we add or multiply, kind of what those look like in our complex number plane. So for number 3, we're going to add the following complex numbers and then graph all 3 parts in our complex plane. So when we add, remember that you're really just combining like terms. So 3 plus 2 is 5, and then 4i plus I is a positive 5i. So then let's graph all 3 parts. So here will be our first complex number that we'll graph, here's our second that we'll graph, and here's the third. So our first 3 plus 4i as coordinates, that would be 3, 4. And I'm going to go ahead and draw in the modulus there as well to kind of illustrate the point. The next complex number was 2 plus I, so that would be over 2 and up 1. So that would be this part right here. So our third part, 5 plus 5i, actually ends up being right here. Why this is kind of interesting to think about, let me go ahead and draw this in here, is actually complex numbers and addition in the complex plane should look familiar if you've studied vectors at all. When you're adding 2 vectors, you should end up at the same place. So if you were to take that 3 plus 4i and then add the 2 plus I to it, you would get there. If you were to flip the order around, you would end up doing the same thing right here. Notice that you're essentially creating this kind of parallelogram, which is also kind of the visualization of how to add those complex numbers. So for those that have maybe seen vectors before, and we haven't talked about vectors, in fact, you probably will not talk about vectors until honors pre-calculus next year. But for those that have seen that in a physics class or something like that, now you can maybe see a connection where complex numbers might actually be kind of useful. Let's go ahead and do the same thing with number 4, except this time let's go ahead and multiply. So as we multiply, let's go ahead and distribute. So multiplying out the 1 should be pretty easy. So that would become 2 minus 3i. And then don't forget to multiply out the I, so a positive 2i and a minus 3i squared. Then we can go ahead and simplify that a little bit. Negative 3 and positive 2 is a minus 1i. The I squared changes negative 3 to being a positive 3. And then we just simplify one last time. 2 plus 3 is 5. So 5 minus I will be our answer. Let's go ahead and graph those 3 parts once again. So here's going to be our first complex number to graph, our second, and then here's going to be our third. So the first 1 plus I is just going to be the coordinates 1, 1. The next 2 minus 3i is going to put us right here. So 2, negative 3 would be the point that you are graphing. So once again, for those that are familiar with vectors, you should be somewhat not surprised by the fact that your product, 5 minus I, looks something kind of like this. So again, it kind of is not necessarily an average, but it does take on a little bit of the distance and characterization of the first two vectors, and then there would be your product. All right, so hopefully that gives you just a little bit better idea of complex numbers, what they look like in the complex plane when they're written as coordinates, how to find the modulus or the distance from the origin, and then how multiplying and adding complex numbers in the complex plane is very similar to vector addition and vector multiplication in the normal plane. All right, guys, that's it for this time. In our next section, we're going to be starting to learn about quadratic functions, so we will do our intro section for that. Until then, have a great rest of your day.